Hello. We are going to talk today about random variables, and specifically we're going to talk about discrete random variables today. We're going to start with a little bit of kind of like a warm-up to kind of get us into the definition of what a random variable really is. So suppose that we toss 3 coins. What is the sample space? So list all the possible outcomes. Well, when I toss 3 coins, each coin could either land heads up or tails up, right? So I could either get heads, 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 tails, heads, tails, heads, or heads, tails, tails, right? Or I could get tails, heads, heads, or tails, heads, tails, or tails, tails, heads, or tails, tails, tails. So there's 8 possible outcomes. There's my sample space. Now, let's pretend, or let's suppose that I'm going to count the number of heads when I toss 3 coins. What's the sample space? So if I count the number of heads, so in other words, I'm thinking about like X being the number of heads when I toss 3 coins. I could either get 0 heads, 1 head, 2 heads, or 3 heads, right? That's my new sample space. Now, if I wanted to come up with the probability distribution of the number of heads when I toss 3 coins, that's all the possible values for X and the probability of each possible outcome. So the first possible outcome, 0 heads, is 1 out of 8, right? 1 head would be, let's see, this one, and this one. So it would be 3 out of 8. And then 2 heads, I'll put like X's by these, would be those 3 out of 8. And then 3 heads would be 1 out of 8. So we went from supposing I'm tossing 3 coins, what's the sample space, to counting the number of heads. Now this is my sample space down here, right? Kind of looking at the same experiment, but I'm defining my variable a different way. So that leads us into chapter 6, talking about random variables. And let's get to this definition. So a probability model, we just looked at one, describes 2 things: the possible outcomes and the likelihood that those outcomes will occur, or in other words, the probability of each. So I just made you a table to represent the probability model of tossing 3 coins and counting the number of heads. So same thing. When we define our variable to be the number of heads obtained, we are going to call that a random variable. So a random variable is just a variable whose value is a numerical outcome of a random phenomenon. So random variable, it just has to be a number, okay? If I'm looking at like hair color, that can't be a random variable because hair color is brown, blonde, black, whatever, right? But the number of heads that you get when you toss 3 coins, that's a random variable because it's a number, right? If I were to just say toss a coin 3 times, that's not a random variable because the outcomes are tails, 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 heads, 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 right? So in different situations, I can look at the situation differently and kind of make it into a random variable. So for example, with the hair color thing, I could say, if I just said record a person's hair color, that's not a random variable because that's like black, red, brown, whatever. But if I were to say count the number of people with brown hair in a sample, then that could be a random variable because I'm counting a number of people. So my people would be 0 people, 1 person, 2 people, right? All right, so random variable has to be a numerical outcome. So We're going to look at probability distributions for random variables, and we're going to specifically talk about discrete random variables today. Continuous random variables we're going to look at another time as well. But just like we have before, our probabilities all have to add up to 1 for all the possible outcomes. Each probability also has to be a number between 0 and 1. So let's look at two different situations. Choose a random number within the range 0 to 2 pi. How would you define the random variable x? So I could say that the random variable x, so I could just say that the random variable x is a number such that x is between 0 and 2 pi, right? What values can x take on? Well, x could be 0. It could be 0.1. It could be 0.001, 0.00001, right? So there's really an infinite number of values that x can take on. There's an infinite number of numbers between 0 and 2 pi. So I can't really go and make like a probability distribution table, right? Because there's an infinite number of numbers between that range. On the other hand, if families having 4 children generate the probability distribution for the number of boys that the family might have. Well, the number of boys, if x is the number of boys in a 4-kid family, x, the number of boys, could either be 0, 1, 2, 3, or 4. So if the family's having 4 kids, they could either have boy, 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 right? Boy, 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 girl. Boy, boy, boy. Oh, excuse me. Girl. Boy, 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 girl, girl. Or they could have boy, girl, boy, 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 girl, boy, girl, boy, girl. I won't keep saying this because it's probably getting annoying. I'm just going to keep writing. And then those are basically all the iterations I could come up with, the boy being the oldest. Now let's flip and have the girl being the oldest. Okay, so there's 16 possible outcomes, right? The probability of 0 boys would just be this right here, 1 out of 16. The probability of 1 boy would be here, here, and here, here, right? So we have 1, 2, 3, 4. So 4 out of 16. Oops. The probability of 2 boys, I'll do X's on these. So it would be, there's 2, there's 2, there's 2, 2, 2, 2. So 1, 2, 3, 4, 5, 6. 3 boys, I'll do like check marks. Let's just check mark. So 3 boys. 3 boys. 1, 2, 3, 4. Those 4 out of 16. And 4 boys would be 1 out of 16. So that's our probability distribution table. And the number of boys in a 4-kid family is a random variable because it's a random phenomenon. And my outcomes are numerical. 0 boys, 2 boys, 3 boys, whatever it might be, right? So these are different though, because this second one, I was able to come up with a probability distribution table, but with the first one, I wasn't. And the reason is because the second one is a discrete random variable. It has a countable number of possible outcomes, as opposed to the first one, is actually a continuous random variable. And so today we're just going to talk about discrete random variables. We'll follow up on continuous random variables. So let's look at an example. I'll leave this up here for a second. Take a minute and read this. So maybe you've heard of an APGAR score, maybe you haven't, but like it says here, every newborn is given an APGAR score. If you ask your parents, they may or may not remember what your APGAR score was, but if you ask them, they might not remember what your score was, but they'll be like, oh yeah, you had one. I can't remember what it was. Okay, so our process is to select a newborn baby at random. So the important part is that we're picking one at random. So it's a random process. And the APGAR score is a numerical value, right? It says between a whole number value between 0 to 10. So this is a random variable, random numerical outcome. So define the random variable X to be the APGAR score of a randomly selected newborn baby. And this is the probability distribution of X. You can probably already see where this is going. See those question marks there? Well, if I needed to figure out what the probability of having an APGAR score of a 0 was, I can use what I know about these are all the possible outcomes. So these probabilities have to sum to 1 or 100%, right? So if I add up all those probabilities that were given to me for all those other APGAR scores, they add up to 0.999. So this probability in here is 1 minus that 0.001. The other piece of this is we need to talk about notation. So write the event the baby has an APGAR score of 0 in terms of X. Well, remember, we defined X back here as a random variable. So I can use that random variable. X is the APGAR score of a random selected newborn baby. So this is that notation that you need to know, be able to read, and be able to use. So the event that the baby has an APGAR score of 0 is like X equals 0. And we're trying to find that probability. So we're trying to find the probability of X equals 0. Notice the X here for random variables are going to be capital letters. And you don't always have to use X. We could have defined it to be like A for APGAR or whatever. Doesn't matter. But typically they're capital letters. Okay, part B. Doctors decided that an APGAR score of 7 or higher indicates a healthy newborn baby. So what's the probability that a randomly selected newborn baby is healthy? So in other words, if they get a score of a 7, 8, 9, or 10, they're a healthy newborn baby. Because those scores are disjoint when you're a newborn baby and you're randomly selected, you can't be an APGAR score of an 8 and a 10 at the same time. I can add these things up. So the probability of a randomly selected newborn baby having a healthy APGAR score is 0.908 or like 90%, a little bit more than 90%, right? Now, again, talk about notation or think about notation. Look at this. We're looking for the probability that X is greater than or equal to 7. So in other words, we're looking for the probability that that APGAR score is greater than or equal to 7. Okay, so now we're going to take this data in this probability distribution table and we're going to throw it into a histogram. So this is what that histogram looks like. And it should kind of make sense. If you look here, the probability of having these low APGAR scores is pretty small. And then when we get up here, like most babies have an 8 or a 9 as an APGAR score, right? So we can see this peak here. In chapter 1, now we're going to go back and revisit chapter 1. We talked about SOCs. We're going to do the same thing here. We need to be able to talk about the shape, center, and spread or variability in with a random variable. And so we would say that this distribution, the distribution of APGAR scores, is strongly skewed to the left. We have a single peak of an APGAR score at 9. But what about, because center spread, because it's left skewed, I need to calculate the median and the IQR. How would I do that? So that's what we're about to talk about now. And if it were symmetric, I'd need to be able to calculate the mean and standard deviation. So just another, before we do that, going back, when we said that a newborn baby would have an APGAR score of 7 or higher, if I were just given this histogram, I could still calculate that by adding up all the probabilities in these bars here, right? So those bars equate to about 90% of all the newborn babies. All right, let's look at another example. So Pete's Jeep Tour, I'll let you read this. So C is the the total amount of money that Pete collects on a randomly selected trip. So it's randomly selected and he's collecting dollar amounts. These are all numerical values. So this is a random variable, right? So he can either collect $300, $450, $600, $750, or $900, depending on how many passengers are in the trip. And he collects that amount of money with each of these probabilities given, right? So we're going to make a histogram of the probability distribution. So if I were to do this by hand, the X variable, or in this case we called it C, but that goes on the X-axis, and the probabilities are going on the Y-axis, right? Tell me about its shape. Think about it. Looks pretty symmetric, right? It looks like the peak is around $600. So if I were to if I were to want to describe the center and the spread, I need to calculate mean and standard deviation, just keeping in mind. So the mean, and we're going to call that the expected value of a discrete random variable, is basically a weighted average. Because think about it, not every outcome is equally likely. Pete is way more likely to have someone who pays $600 for his trip than he is to have someone pay $900. So he doesn't want to just average these 5 numbers. He doesn't want to just add them up and divide by 5, okay? Because we know that he's more likely to get a $600 trip. So this $600 should weigh more than the $900 trip and the other ones, right? All right, so basically, the mean of a random variable, and you also need to know that that can be called the expected value, is a weighted average. How do we calculate a weighted average? Well, we take each individual possible outcome and multiply it by its probability, as you can see down here. Then we take the second possible outcome multiplied by its corresponding probability, et cetera, et cetera. And then we add all these things up. That's how we calculate a weighted average. So that's your formula. Let's talk about notation. And there's kind of a lot to this. Notice we're using a mu for the mean, because think about, let me go back to Pete's Jeep Tours. This is every possible outcome. This is the population. This is in the long run. Pete could collect $300 15% of the time. So of like all the time, right? So this is the whole population. So because a random variable is describing a whole population, oh, I went too far, sorry. We are going to use mu sub x, we call it. So this is kind of indicating that it's not the mean of like individual data points, it's the mean of the random variable x, where x, in the case of Pete, is the amount of money that he collects on a randomly selected trip. Now, we also call the mean of a random variable expected value, right? So this is the notation for expected value. And these two things are interchangeable, either mu of x or capital E of x. They both mean mean or expected value of a random variable. You need to be able to use both. You need to be able to read both, okay? All right, so let's go back to Pete. find the average amount of money that Pete collects on his Jeep tours, or in other words, the expected value. Either one is fine. So the mu of all this, mu sub C, the mean of all the costs, right, or the total collected, whatever, is 300 times its probability of 15%, 450 times its probability, et cetera, et cetera. We're multiplying each individual value by its probability and adding them up, right? So you could check, you could do this on your calculator, but this is kind of a pain in the butt. The calculator, to type this in like by hand, the calculator, of course, we have a shortcut that we can do. But his average amount of money that he collects is $562.50, or we could also call that his expected value. Okay, so if you wanted to use the calculator, which you should be able to, this is how you would do it. You would go into your lists, and you're going to see in L1, I've entered all of the C values, so the amounts of money that he could collect. And then in L2, I've entered in all of the probabilities of the corresponding C values. And here's the important part. These have to match up. So the 300 goes with that 15%. The 450 goes with that 25%, et cetera, et cetera. So you have to make sure that you're putting them in the correct order. After you have your data in to L1 and L2, or L whatever and L whatever, it doesn't matter, you're going to go into one variable statistics. So go back to your home screen, second quit, and then hit stat, calc, one variable statistics. And before now, I've told you to just leave this blank. Well, now we're going to fill that in. So the list, you want the mean and standard deviation in a second, but you want the mean and standard deviation of the data in L1, but you want to weigh it on the probabilities in L2. So where it says like freq list, that stands for frequency list. So what are the frequencies for each of the values in L1? Well, I put those frequencies in L2. So list is L1, wherever you have the data values, and then frequency list is wherever you have the probabilities. When you hit calculate, this will spit out. So the mean of the random variable, or in other words, expected value of the random variable, is that X bar value, $562.50. Just so you know, and we're going to come back to this in a second, but the standard deviation is going to be listed here for at the under sigma. And notice it's under sigma because just like we said, it's the whole population. We use mu. This is the whole population. So for standard deviation, we're going to use sigma. Okay? And we'll come back to that in just a second. But if you scroll down on this screen, it'll give you like the median and all that stuff too. All right, so that's using the calculator. Now let's look. So here's going back to Pete, his Jeep tours, right? So this was his histogram for the amount of money that he collected. And we determined that the average or mean or the expected value of his random variable was $562.50. So if you recall from, again, earlier in the year, the mean is the balance point of a distribution, whereas the median is where you would kind of cut off the 50% mark. So how do we interpret this value? Remember, this is a population of all of Pete's Jeep tours. So here is how you're going to interpret the mean or expected value of a random variable. If we randomly select a lot of his Jeep tours, Pete will make about $562.50 per trip on average. So this is the average amount that he makes per trip. But when I've selected lots and lots and lots and lots of Jeep tours. So when you interpret a random variable, the mean of a random variable, you need to talk about it being random. We're doing this lots of times. He makes about whatever that dollar amount is on average. and it needs to be in context. So the dollars per trip, right? Okay. All right, let's go back to the APGAR score. So if you want to get this data into your calculator, you can pause. So get this into L1 and L2, or you could use L3 and L4, whatever you want. So you're going to calculate and interpret the expected value of X. So the other thing I want to talk to you about is, what do you have to actually write on the paper? So now you know how you can use the calculator. But as you know, we still have to write our work on paper, okay? So even though you're going to type this into your calculator, you're still going to show part of the formula or the calculation that you used. So the expected value of X, or the mean of X, mu sub X, we're going to multiply each individual value, that's 0, times its corresponding probability, plus 1 times its corresponding probability, plus we can use this ... So here's what I would do if I were you. You don't even need this second one. What I would show, or what you have to show at minimum, is the first and the last values with a plus sign and the ... in the middle. You don't have to show the second. You can if you want to. But there's the mean, or the expected value of X. Okay, so you're going to write down that formula. You're going to plug it into L1 and L2. Let the calculator do the number crunching for you. And we're going to interpret. Remember, your interpretation is if you randomly select lots of newborns, the average APGAR score is about 8.128. So randomly select lots of times the number and then the context. So really like 4 parts to that. All right, median. So that's the mean. The median is right like the center point, like the middle point, the 50th percentile. So what you're going to do is you're going to look at your probability values, and you're going to calculate cumulative probability. So starting at the lowest data point, Pete collects $300 15% of the time. So between like 0 and the 15th percentile, you're collecting $300. Well, then the next 40% of the time the next 25% of the time, you're collecting $450. So you're up, if I add 15 plus 25%, you're at the 40th percentile when you're collecting $450. Well, then $600, I collect 35% of the time. So if I add 15 plus 25 plus 35, I'm at 75%. So I want the 50th percentile. So the 50th percentile is somewhere in the in one of these $600 values, right? Because I go from the 40th percentile here to the 75th. So the 50th percentile is somewhere in the middle, somewhere in that $600 range. So the median is the smallest value for which the cumulative probability is equal to or goes over 50%. So his median amount of money is $600. And don't forget, you can also get this on the calculator, but you need to be able, using that one variable statistics, right? But you need to be able to interpret it and show your work. Okay. So for Pete, if we use his mean, right, when we describe his distribution, we also need the standard deviation. So standard deviation is a weighted value. Now this gets a little bit trickier. So let's talk about notation first. I know this looks like a mess, but notation first. We already kind of talked about this. When we have a random variable, we're talking about like a whole population. So we're using sigma sub x. Okay, that's our notation. The standard deviation, or the sigma of the random variable x. Now, here's your formula. And this goes back to the formula for standard deviation that we learned all the way back in chapter 1. Except for now it's weighted. So you take the individual value and you subtract it from the mean. Now the mean, the mu sub x, is the mean of the random variable that we just calculated, that we've been talking about, right? So you take the individual x1, subtract it from the mean, you square it, and you multiply it. Here's the new part. You multiply it by its probability. That's what weighs it. And then you do the same thing. x2 minus the mean squared times its probability. x3 minus the mean squared times its probability. And you keep going dot, dot, dot till you get to the end. Then you take the square root of the whole thing. So the variance is what you get, and again, this is review from chapter 1. The variance is sigma squared. That's what you get before you take the square root. So the only difference between this formula and this formula is in the second one, we've taken the square root. All right, so like I said earlier, you're going to have to be able to write part of this formula down to show your work, but you're never going to calculate this by hand. You're going to throw it into the calculator, into L1 and L2, and then one variable statistics of L1, and then frequency list weighted on L2, and then use whatever it gives you for that sigma value. Oh, why is it not letting me go? Hold on. Hello? There we go. Sorry. Okay, measuring variability, standard deviation. So earlier we defined the random variable x to be the APGAR score, right? So same thing. We calculated earlier the mean of the random variable to be that, 8.128. Let's calculate and interpret the standard deviation of x. So that's that ugly formula. Again, the number crunching is easy. You're just going to pull it off of the calculator. But what do you have to show? So you have to show, if I were you, I wouldn't even do this. I would just say sigma sub x is equal to the square root of the first value, 0, minus the mean, 8.128 squared, times the probability of 0, plus dot, dot, dot. And then the last value, oh, I'm sorry, this should be a, oh, look. My apologies, guys. This should be a 10. So the last value is 10 minus the mean, 8.128, times its probability should be 0.053. And then you don't even need this. I would just say equals that. So I'm sorry this is messy, but so basically the 0 minus 8.128 squared times 0.001 dot, 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 10 minus 8.128 squared times 0.053, and then equals 1.437. Okay. So interpretation, again, a randomly selected newborn's baby APGAR score is typically going to vary from the mean by about 1.437. We just have units here because the APGAR score doesn't really have units. So the interpretation of standard deviation in this chapter is the same as the interpretation essentially in chapter 1, but you're just talking about being randomly selected, the baby being randomly selected. Okay. That's it for discrete random variables. Thank you so much for watching and have a great day.